help everyone. So welcome to our CCNP ENCORE class. Everybody, thank you for being here. I want to first off just go through this little short section before I give you an example I created for us to kind of show you something that's very interesting about BGP. First off, setting up basic BGP is very simple. Remember, you've got to have TCP connectivity between two devices in order to run BGP between them. What port number does BGP run over?
179.
TCP 179, exactly. So if you do not have TCP working and you can't get port 179, you will not establish a BGP neighbor relationship. So for basic BGP, all we really have to do is turn on the BGP process using router BGP AS number. Now, in the real world, that AS number is going to be given to you by an ISP or by INA or by an internet organization. In our labs, we just pull a number out or we just use a number they've given us. Real world, you must use a number that's been assigned to you. Do not use a number that's not assigned to you because that can cause major issues on the internet, okay? You can set your BGP router ID. If you don't set your router ID, it's the highest IP address on a loopback or it's the highest IP address on a physical interface, one of the two, okay? Second thing is you're going to establish the neighbor relationships. There is no way for BGP to send out hello packets. You must tell it who its neighbors are. You must say this router has this neighbor in that remote AS, okay? And then by default, you'll be working in IPv4. You set your network statements and you do the mask and go from there, all right? And then if you want to, we'll show multi-protocol, but you can do sub-address families such as IPv4 unicast and IPv6 unicast. So a very basic configuration here. We have 65.100 and 65.200. They're going to connect to each other. Router 1 does router BGP 65.01, 65.100, and says remote 10.12.1.2, remote AS 65.200, and vice versa. And then you'll notice this here. You'll notice R2 is turning off IPv4 by default and using the sub-address families or using the address families, okay? So that's why you'll see there, we talked about earlier, Clay, you turn off default IPv4 unicast, and then you can use the address families. So these are the same thing. They're exactly the same. It's just one is using the default IPv4, one is using sub-address families, okay? Now, I want to show you a network I made for you. I actually set us up a network, and I want to talk about something really interesting because I set this little network up for us in Packet Tracer, and I want to show you something I think super, super cool about BGP. I made an AS5200 and an AS6200. I've got an R1 connecting to an ISP. Now, we do know that typically with BGP, you're going to be connected to more than one ISP. It's a lab, folks. I'm just showing you a lab. That's it. Okay, so don't be jumping all over me about that or putting it in the comments if you watch this on YouTube. What I'm wanting to show you, though, is this. I want to show you something really cool about BGP. If I go right now and I show you the ISP, okay, so let me pull my ISP over here. And if I go in here and do a do, I got to click in here first. I do a do. Okay. I do a show IP BGP neighbor. All right. You can see that I have a BGP neighbor relationship with a remote router ID of 11.0.0.1. Okay. Which, by the way, that is because I have a loopback on this R1. Let me pull up R1 over here too. I have R1 and ISP beside each other. So here's R1. And let me get ISP. Here's ISP. Okay. So on R1, if I do a show IP and brief, you will see that I have three networks configured. I have the 192.168.12 network, which was an internal network between me and my inside. I've got the 10.0.0.1/30 network that is between the R1 and ISP. And then I've got a loopback 11.0.0.1. So you will see that this ISP has a neighbor relationship with R1 and vice versa, show IP BGP neighbor. And you'll see I've got a neighbor relationship with remote router ID of 172.16.0.1, which is it's my ISP. Now, I want to show you something really cool. Inside of this is to show IP protocols. I want to show you what I've done here. In BGP, I am only advertising right now the 10 network. And over here, I do a show IP protocol. You're going to see that I'm actually advertising the 10 networks here. So if we do a show, let's do a show IP route, you will see that, actually, let me do this, do a show you my BGP configuration. I'm actually advertising 11 and 10, but you'll notice here, I've learned BGP 192.168.12.0. Okay. Actually, that has not fell out yet. Yep, that should have fell out. Hold on a minute. Let me clear BGP. Clear IP BGP star. Now, remember what did I call BGP? What kind of protocol did I call it?
Path vector.
Path vector, but also called it my own name for it's the coffee cup protocol. Because once you make a change, give it a little while, because it's going to take a while for it to come up. All right, so I have in this particular setup, you'll notice that I am, if I do a show IP int brief, show IP int brief, you'll notice I am connected to the 192.168 network. I'm connected to the 10. I'm connected to the 11. So you can understand that being advertised, that this particular router is getting 11 and it's getting 192.168.12 from me via BGP. So I'm advertising those. However, if we look at our picture, you'll see there's another network over here, 204.211.19.0. This R1 is not directly connected to it. Remember, I told you all of our routing protocols to this point, we could only advertise directly connected networks. Well, take a peek at this. We're going to advertise 204.211.19.0 into BGP. We're not going to redistribute it. We're going to advertise it. And BGP is going to allow that, and it's going to advertise it, because if you look on R1, you're going to see that R1 knows how to get to the 204.211 network via an interior gateway protocol. So it's called network layer reachability information. As long as BGP has network layer reachability information, in other words, it knows how to get to 204.211.19.0. It's not directly connected to it. It just knows how to get to it. It will allow you to advertise it into BGP. So let's go back over and let me prove to you, because it's like, show me state, show IP route. You'll see 204.211 is not currently in the routing table. You don't see it anywhere in here. Agreed? Okay. So let's go in here now. Big T, router, BGP 5200. Let's do network. 204.211.19.0 mask. It's a 24-bit mask, by the way. So 255.255.255.0. Hit enter. Now let's go over here and hit up here and do a show IP route. Now look what just happened. We now have the ISP learning about my internal network, and that's not even a network directly connected to R1. That is a network that is actually connected over to the inside router. But because R1 knows about it via OSPF, it has network layer reachability information, it can advertise that up to the ISP. That's what makes BGP not really a routing protocol so much as a routing process, because it's taking information from other routing protocols. Notice I didn't redistribute it. I would expect it to do this. Any routing protocol can do redistribution. That's just taking something external and then advertising it into the other protocol. So it's from one protocol to another protocol. I didn't do that. Well, all I did was I went in and said, I want R1 using BGP to advertise this network. Well, what R1 did is R1 said, okay, let me see in my routing table, do I know how to get to 204.211.19? And it went, yeah, I do. So I will advertise that into BGP. If it didn't know that, it would not have advertised it. It would have failed to advertise. Said, nope, I won't do that. That is what makes BGP so powerful. It's also what should scare the absolute bejesus out of you. And that is because if you mess up and bring in all the ISP routes into your internal network, you can destroy your internal routers. And not really destroy them, but you'll lock them up because they won't be able to process. They'll have so much in their routing tables, they'll basically, it'll cause them to crash. Or worse yet, you're going to allow traffic to go through your network, and then you're going to become a transit network. And that's going to overwhelm your network's ability to do anything. Okay. I want to show you this because to me, that is a super interesting example of how BGP works and how BGP is different than all of our other routing protocols so far. Any questions about that? What do you think about that?
I think it's good, but what if you added just one more router in that into autonomous system 5200?
Okay. So you want me to add another one? I can do that. So let's do this. I'm gonna pull up. Here's my actual. Here's my packet tracer. I still got it running. All right. So you want me to do another router more internal, right?
Yes, another IGP.
Okay. So let's bring out. Let's take and bring another 4321 out here. All right. Let's connect. Let's see. We got the only problem we're gonna have is this. So we'll do it. We'll have to do it like this. I'll do it like this. We go gig 00 to here. All right. So this is the 204, 211 network. So let me bring this up first. So let's do CLI. It's booting. So let's imagine. Oops, click in here. Let's imagine this is a remote. En config t host name remote. All right, line con 0. I do this just to keep me from driving myself crazy. And then I'm gonna do int gi 000 IP add 204.211.19.2. Now I'm just doing that so it can talk to the inside folks. So let's do this. Then we'll do a no shut. All right, so that's going to come up. Now what I'm going to actually do here, here's your question though. You wanted another network all the way inside of here, right, Clay?
Yes, that's correct.
So watch this. Here's what I'm going to do now then. I'm going to bring this in here. We'll drop a switch in here. Actually, it won't matter. That really don't matter at all. Let's do this. So we'll put another whole network in here. We're going to put the network. Hold on. Let me get rid of that. I did the wrong kind of switch. Get rid of the switch. Yep. All right. So let me pull out a good switch, not an actual switch, not a 20. Let me get 20. Okay. Now, all right. So let's take on this router, which is actually our remote router. All right. So let me change the name on it. So this is remote. And I'm going to add a new network totally. So I'm going to add, let's see, int gig gi001. I'm going to add the IP add. Let's do the network 131.107.0.1 255.255.255.0. No shut. Okay. Now, first thing I got to do though, no shut. First thing I got to do is this. I've got to somehow connect it so that remote and R1 can talk to each other. And so right now I'm running OSPF inside. So I'm going to take the remote. I'm going to do router OSPF 1. I got to put two network statements on it. One, I got to put the network statement for 204.211.19.0. 0.255.255.255 area 0. Okay. And then I got to do another network statement of 131.107.0.0 0.255.255.255 area 0. Okay. So now if I do a do show IP route, I should see some OSPF routes in here. So I see the network that I've learned from R1. If I go over to R1, let me pull back up my remote here, side by side. All right, so on R1 now, if I do a do show IP route, I should see some new OSPF routes. I see the 131, see that 131 OSPF route right there?
Yes.
Okay, so now what we've done, Clay, is we've added another internal network all the way over here on the left. Now let's advertise that into BGP. So on R1, all I got to do, I think I'm already in BGP. Let me make sure. Yep, I'm already in BGP. So all I got to do is this. I can literally just go in here and say 131.107.0.0. Enter. Okay. And now let's go up to the ISP. It may take it a little bit. There it is. Already got it. Right there's the route that's been advertised all the way from remote out through R1 to the ISP. And again, that's 2 hops away. But the R1, just the key here, and what is the key for BGP? The key is it has reachability to it. It knows how to get to 131.107 via
Underlying IDP.
Exactly, an interior gateway protocol. It could be a static route, but we were just using OSPF in this case. Okay.
Yeah. Thank you.
Questions about that? Well, that's, to me, that just shows how neat BGP is in that it works in such a different fashion than anything we worked with before. All right. So let's jump back then, and here we can see just some of the commands to verify BGP. Show BGP IPv4 unicast summary will show you messages sent and received. If you're sending messages and not receiving them, I would look to see if you have a problem with bidirectional communication. You may only have one-way communication across the circuit for some reason. This will tell you version number, autonomous system of the neighbor. This will tell you the message sent, received. You've got your last version of the database sent, how long you've been up and down. All of those items are there. Number of prefixes received from the peer would be the state and prefix received. So you notice that with these statements, BGP statements, you do not have to enable BGP for a specific interface. You can actually set it up to where it can be a connected network or a static or a routing protocol, can all be used for things to be resolved. Now, here's what it comes down to when we talk about prefix advertisement. That's the reason I gave you this entire example. When you put this network statement in, it goes into the routing information base and looks to see if there is in that rib a path to that network. If it's a locally directly connected, great. If it is a static route, great. If it's another routing protocol, great. Does not matter. As long as in the rib there's reachability to it, it goes in that local rib database, it's valid. It will then, any outbound route policies, there's a whole section on the next chapter that you go through that talks about how to do outbound prefix and distribute lists and all types of things, okay? But there's all kind of policies that can be placed on outbound routes and prefixes. And then if it is okay with that, it goes to the adjusted rib out and will eventually go out to your peer. But if it doesn't make this validity check, if it doesn't see in those databases a way to get to the network, it won't advertise it. Okay. So here we see again, just using the address families instead of the other. You may looking here on this, I forgot to look and see, Clay, but you may have to put this X address family when you type in your config. Well, you shouldn't have to, it'd be fine. It actually should be fine because it'll pop to the next one when you paste that in. Okay. Now, if you receive routes from a peer, when they come in your adjusted rib, adjacent rib in. If there are any inbound routing policies, they will be applied to it. Then it'll go down and be local rib. And you give validity, next hop check. So, and then if it is okay, it'll go into the global rib and will be locally. And then if you can send it to a neighbor, it will go in through the outbound policies. So these are how things get into the tables on your routers. By the way, hey, David. Here's show BGP AFI summary. So this is showing you, if you want to see like IPv4 unicast, and this will show you all the different routes, the entire database, the local rib on the router. And then if you want to see a specific route, you just do show BGP AFI, so IPv4 unicast, and then whatever network you want to see. And then you can drill down and look for a particular network of how you learned about that particular network. All right. So again, you can do indirect sources. That's what this is here, showing you how you learn from a different routing table, because it is a routing application. It is not necessarily a routing protocol per se, which it is a routing protocol, but it's more of an application because you can install routes from anything, whether it be a static, EIGRP, OSPF, however it learns it. If it's in the rib, it will advertise it if you put it in as a network statement. And that was that whole first example I gave you and why I built that for you. And David, you may want to go back and watch the first 15, 20 minutes or so of this, because I go through a showing an example network that shows actually putting external routes or routes not directly connected to a BGP device into the table and how it works. In fact, we even went so far as we added another route in here and showed how that worked. Okay. All right. So route summarization, we talked a little bit about this previously when we were talking about OSPF, but you can summarize in BGP just like OSPF and EIGRP. You can create a static summary. Remember, anytime you have a summary, it does create a route to null zero for anything that's any route or any particular prefix that's not listed or actually not in use as part of the summary. That way it will go into the bit bucket instead of creating a loop. And then configuring aggregate addresses with a network prefix. So you can actually create a prefix using an aggregate address, and we'll see that. Now, by default, when you create an aggregate address, it does not send the AS path with it. It only sends a summary. So by default, it's a summary. It does not do the AS set. So when we sit here and we do an aggregate, you'll notice you could go in here and do aggregate address 192.168.0.0.255.255.0.0. That's going to have this particular router 2. It is going to aggregate all of its 192.168 networks into that /16. And it will not, with that, actually send the AS path as part of this aggregate or atomic aggregate. Okay. So it'll create a shorter prefix length route, but it will not send the AS path. All right. It also does not include MED or BGP communities in that new advertisement. So you lose some of your actual non-mandatory attributes that are part of the prefix. If you want AS path to stay, instead of using atomic aggregate, you actually have to tell it to keep the path by doing AS set summary only. And then that way it will keep the AS path as part of the new summary address. Okay. We'll also keep the BGP attributes that are part of it. So to try to keep any of those that it knows about. If they're well-known mandatory, they're going to go anyway. But if they're well-known optional, then it would be maintained if this particular version of BGP supports it. Okay. Now let's jump down to BGP with multi-protocol. Now be aware this we're going to cover mainly IPv4 and IPv6. This does also work with MPLS, so MPLS layer 3 VPNs. But we're going to cover mainly just looking at using address families. By default, BGP tries to run just IPv4. If you want to use address families, you turn off that default behavior and you enable address families, IPv4, IPv6. There are basically two families. There's IPv4 unicast, which is the address family 1 and subaddress family 1. And there's IPv6 unicast, which is address family 2, subaddress family 1. All right. So IPv6 unicast. So you go in and instead of putting everything under one area and it just being IPv4, You create your neighbor, you do your ID, you create your neighbor statements underneath your main item, but you turn off the default behavior, and then you can use sub interfaces, or excuse me, sub families, address families. In this case, we have a setup that is only using IPv6. Now, what is weird about this? What looks very weird about this? We're only running IPv6, all right? So we're only running IPv6 in this network. We're not running any IPv4. But what's weird about this, what we're looking at here? Look at your router ID, folks. By the way, you have to set the router ID in this example. Because remember, the router ID is typically the highest IP address on a loopback or on a physical interface. If there are no interfaces with an IP address on it, an IPv4 address, you would not have an ID to be able to run and start or use the process for BGP. But you'll notice it's an IPv4 address. It's always a 32-bit ID. And it could have been 1.1.1.1 and 2.2.2.2. But this is what they use in this case. So this is just weird because your router, and that's something that confuses a lot of people, but your router ID has to be a 32-bit address. It cannot be something different. And if you're only running IPv6, you have to manually set it. You can't let it be pulled from a physical interface or a loopback interface. All right. So when they first start up, the neighbors start sending information. They exchange address family capabilities. Here's an example of just showing BGP IPv6 unicast neighbors. And you'll see that it shows who the neighbor is. The neighbor happens to be this 2001 DB80122. And remote AS is 65200. And you'll see the remote ID is 192.168.2.2 because it's a 32-bit address. Here again, same thing, showing summary, shows the router identifier, shows this local address, shows the neighbors. In this case, R2 has two neighbors because in this example it's connected to R1 and R3. All right. You can see here at least 3 prefixes have been sent and received, or excuse me, received. All right. And this 35 received, 37 sent, that's within the range of being normal. If you had 37 sent, 2 received, I'd start getting worried, or 0 received. Then you wouldn't have a neighbor relationship anyway. You probably wouldn't even see this. Here's the tables, show BGP IPv6 unicast. It shows you the networks that are in the table in that network rib layer. And that shows you shows that the local router is generating that prefix. All right. So it's just like a local route. And then you could summarize. You'll notice you can do the same thing with IPv6 as IPv4. Summarization to me in IPv6 is a little bit harder because you got to get into the hex and think about the hex. You'll notice here that if you had a summary address of only 2 bits, it would summarize 0 through 3. If you do 3 bits, it's 0 through 7. 4 bits, 0 through 15, basically, and so on and so forth, all the way through, and can keep going. I am not very good at IPv6 summarization. It's something I struggle with a little bit, and I really have to spend some time when I'm thinking about it. Luckily, you don't see a whole lot of it. You see it in the real world. You don't see a whole lot of it in the labs or in the exam. Just be aware it's available and it's there. In real world, you want to summarize. The goal would be, the true goal is that we could summarize to maybe 5 routes to all of Europe for IPv6, 5 routes for all of Africa, 5 routes for North America, 5 routes for South America. Now, we'll never get it that clean, but if we can get it anywhere below 800,000, we're doing well, because the IPv4 has around 800,000 plus routes in it for the global routing table. Questions? Questions about our little example I gave everybody? Any questions on that? Okay. If not, I actually want to jump. We don't have a whole lot of time, but I do want to jump ahead, and I want to look at 13. I want to jump ahead to multicast. and spend a little bit of time on multicast because it's one of your exam objectives. It's something you've had very little experience with in the past. First off, what is multicast? We've got 3 ways of communicating. We have 4, but nobody talks about the one.
Broadcast, unicast, multicast.
Unicast, broadcast, and multicast. Okay. Unicast 1-to-1, broadcast 1-to-all, and multicast is 1-to-some or 1-to-a group. Now, multicast is a way for us to be able to send information to a group of devices without every device in the network having to see it. Now, we do this through multicast addresses, which are in the 239 range, and we'll show you those in a minute. 239.0.0.0 to 243, I believe it is. I think that's right. But we have Internet Group Management Protocol we're going to talk about. And what this allows you to do is let you set up a multicast source and then have the multicast traffic flow through your network. And if done correctly, it's only going to flow to the parts of your network that need to receive it, and only the hosts that want to receive it will receive it. And we're going to talk about how all this works together using first hop router, a local multicast router, and then using the switch and the ability to do IGMP snooping, which is basically figuring out what particular multicast groups are on what ports, and then getting it down to the receiver. Traditional, this is what we had before: 1-to-1, 1-to-all, 1-to-many. In a unicast video feed, you would have to send a separate feed to every single device, okay, which is a huge waste. In a broadcast feed, you would send it to every device, which is still a waste because not every device needs it. Not every device wants to see it, and they would still have to process it and dump it. So when those broadcast packets came in, plus even getting a broadcast to go across the router is very hard to do because routers don't forward broadcast by default. Imagine too that workstation A and B actually did not want to see the video. With IGMP and with multicast, we can set it up to where those two wouldn't receive it and everybody else would. So be aware with multicast, we can set up things like this. We can set it up to where multicast will flow through the network only to the places it needs to go to and only to the hosts that need to see it. Okay. So the multicast packets, it says here discarded at the NIC level, yes, but if you put a switch in here, it won't even get to that particular host. There's a switch in this network right here. So multicast provides 1-to-many using a multicast distribution tree. And the server only streams one session, one using a special destination IP address. And then the host joined that particular group by taking that IP address and converting it into a special MAC address that they also listen to. So when we look here, it's 224 to 239. Okay, 224 to 239. Sorry, I had a brain fart on that one. So anything in that range from 224.0.0.0 to 239.255.255.255 is part of the Class D range, which is set aside for multicast. There are some special multicast items on here. You can look through those. I'm not spend a whole lot of time.
Are those addresses going to be on exam?
I would know 239 to 240 or 224 to 239. I wouldn't worry so much about knowing every single one of these. It's more important to know how you get a MAC address for multicast from a multicast IP address. Okay, we're going to talk about that right now. So first off, the first 24 bits of any multicast address is 01005E. So if you see that in a MAC address, it's more than likely 99% going to be a multicast packet or a multicast frame. Then what happens is you take the 25th bit is always 0. And then whatever the last 23 bits are left over from the IP address, they are placed into the MAC address. So if you had the multicast address of 239.255.1.1, it would be changed into this MAC address, 01005E 7F0101. So just remember, it's always 01005E. 25th bit's is 0. Everything else are the same bits as the IP address. And now what happens is when the host joins that particular group, it starts listening on both that IP address and on that MAC address. So for all intents and purposes, it's like you've got a new MAC address on your device. What could mess this up? What security feature on switches could be configured in such a way that would keep you from being able to join another MAC address?
Would it be port security?
Port security. If you had set your PC to only allow one MAC address, and suddenly your host is trying to talk on multiple MAC addresses, what could happen?
That would make it.
It could shut the port down if you had it on shutdown. All right. So be aware of that. Be aware that you can cause problems with that. It's another issue you need to think about. Now, it's also possible because of the way this is mapped that two separate multicast addresses could overlap. So 239.255.1.1 and 239.127.1.1 actually end up being the same MAC address. The difference would be there. They would listen on the same MAC address, but when it got up to layer 3, it would be discarded because the IP address would not match. So imagine two sets of hosts, one listening to a multicast stream on 239.255.1.1, one listening to a stream 239.127.1.1. They're on the same segment. Yes, they would all get the frames from both of these, but as soon as it went up to layer 3 to be processed, though they would only process the ones that matched the actual IP address they were listening on. Okay. So we have a special protocol, Internet Group Management Protocol, that is used to basically determine who will join certain multicast groups. When a receiver wants to receive a specific feed, it sends an IGMP join using a multicast IP group address for that feed. And then the receiver reprograms its interface to accept the MAC address of that group address, just like we said before, just a second ago. And so if the PC joined 239.255.1.1, it reprograms its NIC to also receive or to receive that and its normal NIC. Okay. There are 3 versions: IGMP v1, which is very old and not even really used; IGMP version 2, which is most common; and then IGMP version 3, which is used with some source specific source multicast. We're only going to talk about 2 and 3 in this particular section. Okay. Here is an IGMP v2 packet type or packet format, message format. You'll see it's always sent with a TTL of 1 so that they're only processed by the local router, not forwarded. That's so they won't pass through. They're not designed. It's always supposed to be between the router you're connected to or your next upstream item in the multicast chain. These are just the different flags. If you do a general membership query, by the way, that goes to the all host, which is 224.0.0.1. You will learn about some other specific addresses like 224.0.0.10, which could be a rendezvous point. We'll talk about that later. Yeah, pretty much. Let's see. So if you want to join a multicast stream, you send an unsolicited membership report, commonly called an IGMP join, for the group that wants to join. That message is sent upstream using PIM, which is Protocol Independent Multicast Join Message. And then once that local router starts receiving the multicast stream, it forwards it downstream to the subnet where the receiver requested resides. Okay. You also see it can send periodical general membership queries into the subnet to 224.0.0.1 to see if there's any other members on that particular subnet part of the particular stream it is sending. If not, then obviously it would just continue to send it to the ones that the subnet it was sent to. Snooping. Big thing about snooping. Snooping is on your switches. So what snooping allows you to do, it allows the switch to look and see what multicast groups are on what of its ports. So it will learn what MAC addresses for what groups are on individual ports. So if a stream comes in and a particular port is not part of that multicast group, it won't send it to that port. It will only send it out the ports it's supposed to be on. And that's called IGMP snooping. You can do it with a static MAC address entries too, but it's much easier with snooping. So you'll see here, IGMP snooping, we've got two hosts, workstation A, workstation C, that we want to receive this multicast stream. The other two, we do not want to receive the stream. So you'll see that gig 00 and gig 02 would be mapped to 01005E 7F0101. So in other words, it would say any frame that comes in from R1 destined to that multicast group will go out to workstation A and workstation C. But because G01, G01, G03 or workstation B and D are not part of that multicast group, and using IGMP snooping, the switch learned this, it would not send it out those two ports. So you can see how multicast becomes much more efficient than a broadcast, because now workstation B and D don't even know the multicast is really going on. They're just sitting there going, waiting for traffic. All right. Does that make sense? Here's our snooping again. It's basically set up like we talked about. Switch 1 receives the traffic. It forwards it only out gig 01, gig 0002, because those are the only two ports that had an IGMP join request for that group. You can also do it statically if you want to, but it's not scalable because it would take forever to put that in on all your switches. It's doable though. You could do it, but it's not. But IGMP snooping is the way to go. Okay. Now, because multicast is a specific type of traffic, there has to be a way to route it through your network. So in other words, it's got to go through your routers. Protocol independent multicast is a way to do that. It allows you to locate multicast streams and forward them to the correct destinations across multiple routers. It is a multicasting routing protocol that routes them between network segments. It can use any of the unicast routing protocols to identify the path. So in other words, there's still got to be a path underneath that it can pull from, kind of like BGP, but it can use any type of unicast routing protocol underneath to make its decisions. But there has to be something there. If there's no route there, it can't go and find its own. Now, what multicast routers do is they create what is called a source tree. And that tree is defined as a distribution tree. And then we find what are called S, G, source group, source, group. So our source up here is 239.1.1. It comes down, source is 10.1.1.2, that's source. The group is 239.1.1, 1.1.1. Keeps going down, same thing, source 10.1.2, 239.1.1, so on and so forth, on down until it gets to all of the different devices that need to participate. These devices, R3, R4, would have received an IGMP join request from receiver A and receiver B, and then they would have sent that using PIM upstream until they could find the source saying they were part of protocol independent multicast. All right. Now, folks, I'm going to stop right here and we'll pick up on shared trees, rendezvous points, and all those next week. So if you haven't read the section on multicast, go ahead and make sure you read that. Oh, it's okay, David. David had to take off. If you haven't read that part on multicast, and we'll talk about it next week. But I want to stop here, and then we will resume that next week. Okay. Any questions?
No.
Hold on one second. I'm going to stop the recording here first if there are no questions.